Good evening. Welcome to the week 7 doubt clearing session on fundamentals of additive manufacturing. Am I audible to you? Or is there any
Yes,
background
ma'am.
noise coming?
No.
No. Okay, fine. I'm sharing my slides. I hope it's visible. So, for last 2 weeks, we got to know about the liquid additive manufacturing processes, such as vac photopolymerization. Then we got to know about sheet lamination, which is a very different kind of additive manufacturing where we do both subtractive and additive, and we get the final geometry, which is mostly used for the prototyping purpose. Today's this week's lecture was based on the wire-based additive manufacturing. Today we are going to talk about FDM, fused deposition modeling, and next day we will be talking about another wire-based additive manufacturing, which is called wire arc additive manufacturing. So in wire-based, few things I want to point out. First is polymer and metal both are possible in wire additive manufacturing. In the classification of additive manufacturing, if you remember the 7 classification according to the ASTM standard, then there were one process called material extrusion, and the second process was called as directed energy deposition. So these two processes can be worked with metal and polymers. So material extrusion can be used for metal and polymer both, whereas directed energy deposition can be worked with only metal. So this FDM or fused deposition modeling is a type of material extrusion process. So just remember that when you are talking about fused FDM or fused deposition modeling, if somebody asks you what is FDM, you just tell that it's a kind of material extrusion process. First thing. And in that, we have two processes. One can print metal, one can print polymer. However, we will gonna talk about only the FDM, which can print the plastic parts or polymer parts. And in case of metal, we will be talking about directed energy deposition, which is this WAM, wire arc additive manufacturing. So the state of the art is directed energy deposition, and the process name is wire arc additive manufacturing, capable of printing metals. So now, okay. So now we will start with FDM or fused deposition modeling. So the state of the art is material extrusion. The process name is fused deposition modeling. So again, if I classify now this wire-based aim into different parts, then we can have materials, material flow, material machine kinematics, energy source, and support mechanism. So in material, we can do polymer, metal, both. Wax can also be possible. It's not very renowned. Material flow, so it can be continuous, it can be drop on demand. So in case of wire-based aim, if you're talking about plastics, then you will get a melt pool, but it's not fully liquid because its viscosity is higher. So it will be kind of the toothpaste, like the semi-solid or semi-liquid state. It's not fully liquid. But when you're talking about a wire, then again the process is same, but it's more liquidy in case of wire. So as the wire comes from the from the wire feeder, it gets deposited over the bell plate. So it can come continuously or it can come drop on demand. Drop on demand means drop by drop it is coming wherever it is needed. And continuous means continuously the nozzle is moving and the wire is coming. Drop on demand means the nozzle, from the nozzle, the drop by drop, the wire is coming as a melt pool or as a melted wire is coming, and it's getting deposited on the bill plate whenever it is needed and in a droplet format. Next is machine kinematics. It can be serial kinematics, parallel kinematics, or hybrid. It's just like how your degree of freedom is told to the machine, how you have set the degree of freedom in the machine. What are the parts that are moving? Whether it's the bill plate that is only moving, or whether it's the tool head, the wire feed feeder, or the nozzle from which the melted wire is coming, that is moving, or both the things are moving. Then our energy source. So energy source is that resistance, heating, induction heating is not that much common, this too, but arc is very much common. From arc, we have the YM process, which is wire arc additive manufacturing. Then we have energy beam. Energy beam means, for example, laser. So in previous class, we got to know that laser can cut the sheets, the wooden, metal, or plastic sheets in case of sheet lamination. Similarly, we also got to know that laser can also cure the resin in case of wet photopolymerization. So the purpose of using laser in last two processes were very different. For this process, the use of laser is similar. Like the laser will actually melt and solidify the powder or the wire. So here we are talking about wire. So wire. In case of wet photopolymerization, also laser was used to cure the liquid resin. Here also said laser will be used to melt and solidify the wire. That is the energy beam. Then we have support mechanism. So if you are printing the polymer with a dissolvable support structure or support material, then you can just dissolve it in water, or you can dissolve it in acid if it's acid dissolvable. Then no support is also possible if your kinematics is very complex. That is, your build plate can move in XYZ direction, and your tool can move in other axes like the tilting and angle, or vice versa, or both. If these are possible, then you can print without any support, even if your part is having a very high overhand structure. Now comes the fuse deposition modeling, which is one process example under the umbrella of material extrusion, where we use polymer as a material, continuous feeding of the material, serial kinematics, very simple XYZ movement. Then resistance heating. So it's basically heating coils will be there to heat the wire of the polymer, and so that the wire can get melted and deposited. Then water dissolvable support you can use. Otherwise, you can use the same material support, and later on you can cut the support from the part. So this is the process steps. So creation of CAD model, we know the step. Then slicing, area filling, we know. Then deposition of buffer layers, deposition of main support material. So buffer layer is not always there in every machine, but this is the main thing: deposition of the main and the support material, surface finishing, removal of the support. So this is the overall mechanism. These are the pinch roller. Pinch rollers are nothing but, if you have seen sugar cane and how the street food, street shops of sugar cane juice, if you see the machine, there will be two big wheels which are rotating in the opposite direction and which are pressing the sugar cane also. So from take an example, from one side you are pushing the sugar cane, and because of the pushing of the roller and rotation, the sugar cane is coming outside the roller with squeezed, and the juice is coming out. So here, same mechanism, this pinch roller will try to push and rotate, so that for the rotation, due to the rotation, the wire will move, and due to the force, the wire will be squeezed, and it will come out of the pinch roller and uh, go inside the heater. heater or the liquefier means where you're putting the resistance heating. You have put the coils, these are the coils, this black are the coils, and you're just hitting the metal so that from this teeny nozzle out pipe or something like the tip of the nozzle, from the tip of the nozzle, your melted wire is coming out and you're printing it continuously. Like if the head moves like this, your wire will get deposited like this. Generally, in case of wire additive manufacturing, where it's continuous feeding or any wire additive, your surface will be very much even. There will be no high peak and valleys and undulations or the waviness. The waviness will be there, but it's very little. In case of wire art, your surface will be good in comparison with the powder-based additive manufacturing process. So quickly we'll see the feeding mechanism. So feeding, as I said, that the typical feedstock are amorphous thermoplastic polymers filaments with a diameter of about 1.5 to 3 millimeter. 1.2 millimeter is also one diametric wire, which is very much useful in FDM or in WAM process. 1.2 is also there. 1.8 is also there. So then the feeding, we have already understood how the pinch roller is pushing the wire below. So these are the groove tooth, which is actually from the groove the wire is passing, and because of the force and rotation, the wire is coming outside. This is the actual photo of the pinch roller mechanism. So here, how much force you are giving or how quickly you are feeding the wire inside pinch roller is one thing. And how much speed is there in the pinch roller rotation is one thing. These should be in sequence so that the wire will be always in tension and the wire will not buckle up on top of the pinch roller. Like if this wire is coming from the roller or this wire is binded somewhere, and from there you are releasing the wire. So the wire is coming inside the pinch roller. Now, if you release too much wire, then it will be buckle up here like this, the wire. So you have to maintain the speed at how much speed you are feeding the wire. So that is the feeding speed or feed rate of the wire. How much speed the pinch roller are having, like the rotational speed, that is also one thing. Based upon that, how much speed this wire is having after squeezing is the resultant. So that is also important. And all these three, four things should be together to maintain certain tension in the wire. So these are the formulas for that. So you need to note down these formulas. These will be used for the MCQ questions. This formula is also important. So these are the equations through which you can get how much force you are having at the end, how much the motor power should be to for the feed rate to maintain, then what should be the motor torque for the feed rate to maintain. So that here also there will be no buckling, and here also after pushing down the wire, there should not be any buckle. Then the wire will be broken from here. So already we have studied this buckling load in our BTech time. So the same formula is used here to calculate the tension. Now comes the liquefier dynamic. Liquefier is the part where now this squeezed or tension wire is getting semi-melted. So the liquefier design is also very important. So it has three portions, D1 portion, where then lastly D2 portion, and in between there is a nozzle shape. So the liquefier or print head is the part of the machine where the solid polymer feedstock is melted and pushed through a small print nozzle. The dynamics of liquefier is quite complex and challenging to model as melt properties are a non-linear function of temperature and shear rate. So as you're pressing the wire, you are heating the wire, you are melting the wire. At the same time, you're also releasing the wire from the binded roller, and the wire is getting some feed rate, the wire is getting some printing speed also. All the things are happening together. So all these equations are interlinked with each other, and these all also depend upon the property of the wire. So your process parameters are the temperature of the heating coils, how much temperature you want to achieve. For example, PLA is a well-known material for FDM process. PLA means polylactic acid. So that is a very well-known plastic for printing in FDM. PLA, when we use PLA, generally we keep the temperature as 180, 190, 200 degrees centigrade. 190 is the typical average value. But when we use the hyper PLA, a little bit extraordinary property with the PLA, we maintain the temperature as 210 degrees centigrade. So there are variation in the temperature. So heating temperature is one thing. Next is the feed rate. How much feed rate we should make, how much we should release the wire so that the pinch roller rotation can be adjusted, or the pinch roller rotation can adjust the velocity or the printing speed. So feed rate is one thing. Feed rate means how much wire you are providing in a minute, and then printing speed, how much with how much velocity this nozzle is moving from one point to another point. That is the printing velocity. Both are important, and these are the typical process parameters for the printing. So these process parameters depend on the melting point of the plastic. Plastics also have the glass transition temperature. So those are also need to be studied, but melting point is enough in this case. Then how much viscous, or what are the property? If you over melt the wire, it will be still melted or it will just burn away. So that also you need to consider. Then how much is the viscosity of the wire? If it's very much viscous, then you need to you need to adjust the feed rate and the velocity accordingly. So these are few property of the wire that you need to study. Based on that, you need to choose the process parameter. And these are the equations through which, these are the very basic equations through which you can get how much force you need to put, how much motor torque, motor power should be. These are important when you're making the machine, when you're manufacturing the machine. But when you're printing the wire, it's not that much important. So using power law, we are deriving this pressure drop, total pressure drop, because this is a bit thicker, this is a bit thinner, so there will be pressure drop so that your wire can come out of the nozzle nicely and it can get deposited. So that is also having a big equation, and this is important. You need to note down this equation actually. This can come in your exam. Then melt properties. So how, what type of, or in which state your melted wire should be when it's coming out of the nozzle. That is also important. It should not be over melted. It should not be under melted. As I said, it's something like the toothpaste texture. I cannot say it's fully melted, but it's even more than semi-melted. So that condition is important, that how much you need the wire to be melted. So for that, you need some heat transfer equation as well to solve how much force you need to put and how much feed rate you need to. So these are some example problems you can solve later on. These all are on the liquefier. And liquefier problems are actually very big. So these problems actually came in previous year, two previous year questions. So it's better to solve these problems and write down all the formulas. Now, if I go to the next module on fused deposition modeling, does anybody have any doubt? So here we are going to talk about how you are printing from this thing. So here you can see there is a dice well. So this part D2, D3, these are the diameter which is shown here. And if you have the die swelling structure in your machine, then how much the, I mean, we have talked about the continuous, and now if I talk about the drop on demand, the architecture will be a little bit different. And based on that, you can select how much volume flow rate of the liquid can come out of the nozzle depending upon which type of nozzle you are using. This is the printing nozzle. So you have to find out how much will be the flow rate of the melted wire coming out of the nozzle using this equation. Now there is something called bead ironing. Is it here? Anyway, something called bead ironing. So what is bead ironing? So it's important that when your nozzle is this much, this is the droplet that you are getting. Okay. So if from the nozzle your droplet is coming, it's not droplet, but it's that semi-melted wire. When it's coming, so you can put, for example, your nozzle looks like this and your wire is coming like this. If you put your build plate here, you can get the deposited bead like this. You can put the build plate a little bit far away, or you can put the build plate just as the layer thickness. So there are three cases. Three cases will give you three different results. So now we are talking about the stand of distance. Stand of distance is also important because based on stand of distance, you are going to calculate, you are going to get the quality of the build. So as I said, in case of wire-based additive manufacturing process, your bead or the surface structure or the roughness is not that much. There will be some waviness, but not that much bad surface. So it's important to control the process parameter to get that smooth surface, because as much as you lower the post deposition cost, you will ultimately lower the whole printing cost. So that's why we do not want to do a lot of post processing. So that's why we are concerned about the process parameter. So here, if you see, if the head movement or the head position is here, you are getting this type of bead here. The bead is continuous. When your head is this much and head speed is 0.5, your bead is like this. And when your head speed is 2, your bead is like this coming. So it depends. Feed rate is one thing and velocity is another thing. Here it's shown the velocity of the printing. So printing speed is the one process parameter, and based on the printing speed, you will get the shape of the melt pool or shape of the wire which is coming out. Bead ironing is also one thing. So when you print like this, in this case or in this case, you can get uh, the upper surface of the bead not to be having very much high waviness. Your bead can be iron or your bead can be flattened. So at the result of which you will get a very flattened surface and not much waviness will be there in your printed part or in your printed surface. So that is the application of bead ironing. So you can read this portion. Obviously, I would recommend you to go through the lecture videos first if you haven't yet. Then you can read the notes. It's very nicely written here. What are what things. So now this is the thing I was talking about. When the print head nozzle is in contact with the deposited bead, it was found to be beneficial, resulting in more stable flow, ensuring a flat road surface. This is what is happening. When this is happening, like your nozzle is here and your deposited bead is like this, then your ultimate surface will be this much waviness, having this much waviness. But when you're doing this bead height equal to the standoff distance, you will get the very flattened bead. And from this, you can get how much speed you need to have. Because if you lower the speed, your bead height will increase. If you higher the speed, then your bead height will decrease. So you need to find out an optimal velocity for your application, for your printing, whether you need high speed printing to optimize the time or you need a very high quality printing as per your application. Now, the next thing is bonding. Now, when you're, I was talking about one bead. One bead means, for example, my pen is my nozzle. My nozzle went from A position to B position. So the deposition has taken place. And this is one bead. This is the cross-sectional view. Now I'm drawing the top view. This is the top view. In top view, what you'll see, there will be a bead like this. Just one way. It went one way from A to B position. So this is what you'll get in printing, in result. Now you need to print the whole layer. So you need to print another bead adjacent to this. Now, whether you'll print like this is the cross section. Your first bead will move like this, and then your bead will move like this, or you will have some overlap. This is a different picture, but I'm just showing you for an example. You will print like this, you will print like this, you will print like this, or you will print like this. So that is the bead overlap. That is also very important. So this is called the overlap percentage or the hatch spacing. So bead hatch spacing is another process parameter which is not mentioned here. Just I'm telling you because the hatch spacing is also very much important in case of this bonding formation. So when you are doing the multi-bead to print a layer, your hatch spacing is important that how you're going to print the bead as one adjacent to another. If you are doing this configuration, then you'll get a big porosity in between two beads. If you do this, it's very good. If you do this, then there will be overheating of the previously deposited bead because there is so much overlap. This is the overlap between two beads. There is so much overlap, which is not needed. And if you do this, again, there will be porosity here when you will print the next layer. So this is a good configuration. Now we are talking about bonding. We are talking about two droplets. So in case of metal extrusion, the thing is different. In case of plastic in extrusion, the thing is different. Because in case of plastic, there is the polymeric chain reaction is happening or polymeric reaction is happening. In case of metal, there is the atomic bond which is happening. So it says that when you print these two droplets, first these two droplets try to get attracted to each other because of their viscosity. Then they get the surface diffusion and neck formation. Then after randomization, you get this nicely shaped bead, one another or droplet, one adjacent to another. The initial contact between rods of radius A is this. After that, the neck formation happens when they try to get diffused with each other. Then eventually you get the whole bead. So in this is a part of this bead. For example, this is this thing. This was my bead, and one part of the bead was looking like this. How the droplet in case of bead is getting fused with each other to get the whole bead or track. Bead is also called as track. Few equation to prove what you are claiming using the mass transfer and heat transfer formula. Now, there is another very important point is start, stop, and turn. When you start the process, because of the inertia, there can be this bulk. Then, because of the acceleration, your bead will be lower in thickness. After some time, it will be stabilized. So you will get a overally almost same thickness and width of the bead. When it ends, it will try to end here, but because of the inertia, because the material is coming and all on a sudden you're stopping the machine, so it will deposit a huge lump of the material. So that is the process. So to avoid this, what you need to do? You need to stop the machine. You need to stop the feed rate here, but you need to stop the machine here so that this portion will also be flattened and not like this. From here also, you need to start from here, start the machine from here, and start the feed rate from here so that this portion will also be flattened. So these are some cure and optimization techniques that we follow during printing to get a very flat bead or flat layer. Now, surface roughness is also one thing. If you want to print this type of part, it's the wire-based deposition where the layers will be very much distinguishable. However, in case of wet photopolymerization, it was not like so. In case of powder-based additive manufacturing, we will be talking about powder-based later on. The thing is not like so. But in case of sheet lamination, the thing was same. You can distinguish the layers in your naked eye. And in case of wire-based additive manufacturing, in any wire-based additive manufacturing, you can clearly distinguish the layers in between your or in your part build. So these are the things. So if you want to optimize it, you can lower down the layer thickness so that your layer, that distinguished layer marks will be less visible and you can do a minimal post processing to reduce the surface roughness, increase the surface finish. So now comes the design parameter, how you are going to put this layer so that this hump will not be visible that much and your layer can become this smooth. So these are the equations you can follow. Now comes the polymer based process with continuous but parallel kinematics. So parallel kinematics means your excuse me, your nozzle was mounted on a lead screw and it was moving up and down. If it was mounted on a CNC, then it can go and then go down like X, Y, Z. But here it's parallel kinematics. So these three are the joint of this tool. This tool is having these three joints, which three joints are parallel to each other and they can move up and down uh, simultaneously. So depending on which you can move your nozzle very much freely on top of the build plate. And this is just an example of it. Then comes the hybrid. In case of hybrid, it's the parallel kinematics and it's also mounted on the CNC, which is the serial kinematics. This is the serial one, this is the parallel one. So parallelly also it can move up and down, and because of this, it can go XYZ as well. So this is obviously the better configuration. Now comes the drop on demand part. Drop on demand is nothing but there was a video in instead of continuous feeding, the melted wire is coming in a droplet format, the spray format. It can be globule, it's mostly globular format, but in case of polymer, it's not very significant. The droplets are coming whenever it is needed. The continuously wire feeding is not present in this case. So by this, we end the second PPT or PDF. Now comes the third portion where we are going to talk about the metal wire AM process. So in case of metal, things change because now your temperature is going to increase. Your pinch roller mechanism is going to be more strong because now you're squeezing a metal, not a polymer. Uh, Drop on demand is not that much famous in case of metal. It's more famous in case of inkjet printing. So there is another printing method, inkjet printing, which is also capable of doing some MOEMs on MEMS device fabrication using some ink in 3D manner, like 3D printing. There, this drop on demand process is more useful and famous. In case of metal, it's gonna be mostly continuous feeding. Any kind of kinematics can be there, serial, parallel, or hybrid, not of our concern if you are just concerned about the printing quality. If you want to build the machine, then you have to be concerned about this kinematics portion. The energy source is induction arc or energy beam. So let me tell you, in case of FDM, material extrusion, you are not going to use any arc or energy beam because that comes in the directed energy deposition part. So in this case, these are used in case of DD, state of the art. This is used only in case of material extrusion because there are two classification which can print wire. One is material extrusion, next is the directed energy deposition. So in case of material extrusion, your heat source will not come out of the nozzle or will not come out of the machine. It will be inside the machine and it will not interact with the material directly on top of the build plate. It will interact with the material already before coming out of the nozzle. So that is the main phenomena of material extrusion. So that's why induction heating is the only way how you can melt the metal. Yeah, resistance heating you can also do, but there it's not very much possible to reach a very high temperature because for metal you have to obviously go to the higher temperature, at least 500, 600. So that's why induction heating is the option for it. For support, water dissolvable support is not that possible because it's metal and you cannot put a polymer support into the metal part printing. So acid bath is one thing. So if you put 50% HCl, for example, if you make a 50% HCl solution, uh, it can dissolve the steel surface. It can dissolve the steel parts. So like that, if you are printing the copper part, for example, using FDM or material extrusion, you can print the support with steel and then you can go for the acid bath. In acid bath, copper will not be will not harm, like the acid bath will not harm the copper, but it will dissolve the stainless steel. So like that, you can use the acid bath in case of removal of the support. And no support is also possible if you're using parallel kinematics or hybrid kinematics along with the build plate, which is having more than 3 degrees of freedom, then no support printing is possible. So these are two examples of part made using VAM process or the metal wire additive manufacturing. This is the patented. So this is the first machine which were against which the patent was filed, in which the names are not given here. Anyway, we can try to understand. Ah, it's a pencil sketch. I cannot understand. I can see the wire coming, and then yes, this is the nozzle. I think this is the wire. This is the wire. This is coming through the pinch roller, and then through that it's printing here, something like that. Next patent came with another setup of the machine. Then we have more setups of the machine because wire additive manufacturing is the first additive manufacturing patent which was filed in USA. So that's why there are various designs given for this machine. Let's go to our concerned thing. This is a very important thing. So I would like to talk about this. So if you see a shaft, this is a shaft, and there is a worn out portion in the shaft. So directed energy deposition actually came from the process called cladding. Cladding is a process through which you repair the worn out portion of any metal parts. Cladding is basically putting a layer or few layers of the material onto the worn out portion so that it can be reused again. So that is the concept of cladding. And using the concept of cladding, people invented DD, direct energy deposition, with powders. By doing hundreds of layers of cladding, you can get a part. So that is the concept. Using wire also, you can do the cladding, and that's what is shown here. These are few parts printed using metal wire additive manufacturing process previously. You can go through the video, you will get to know about what these parts are, what these patents are about. Then comes our metal continuous all this. So we are going to introduce one process, which is the wire arc additive manufacturing using arc, where we are going to use the concept of welding, metal inert gas welding, tungsten inert gas welding, plasma arc welding. These are the welding process. Welding is also depositing material into the join of two metal sheets or block to join them together. So you are also depositing metal in welding. So why not depositing the metal in 100 times in X direction and then 100 times in Y direction, and ultimately you get a 100 cross 100 cube. So that is the additive manufacturing, 3D printing. So using the welding concept, people invented this wire at aim process. Wire beam aim is where you take laser energy or laser beam or electron beam as an energy source, so LB or EB, to get the wire melted. Shape deposition manufacturing does not use conventional slicing. In fact, it is segmenting rather than slicing. So this shape deposition modeling is nothing but you can break the whole part into few shapes, and then you're printing one shape after another. It's difficult to demonstrate in this slide, but you can get a video in the lecture. So now, if you talk about the TIG and MIG, we know the if you're from mechanical, I think you know the basic concept of MIG. That is, the arc is coming, and then you obviously you have the plus and minus source electrode you have joined with your arc giving electrode rod and the metal wire. If it's MIG, metal inert gas welding, then your metal wire is itself a consumable through which the arc is also coming. So you're putting the arc in it, you're establishing the arc, and then you just move this in this direction so that your metal get melted and deposited over the build plate. In case of TIG, your uh, wire is just there to produce the arc, and from here you provide the metal wire which will eventually get melted and deposited over the build plate. And tungsten will be there as an electrode to produce the arc. That is the concept of TIG and MIG, and this is how you can print in additive manufacturing process. So in case of TIG and MIG, your metal transfer will be a little bit different than how you were transferring the metal in case of fused deposition modeling. Because in case of fused deposition modeling, there was this concept was called bead ironing, if you remember. There was this concept called the bead bonding and spreading and modeling. These were possible because your heat is inside its material extrusion. So you can print the metal semi-melted, semi-liquid wire, whatever way you want to print. But here you have to establish the arc. If I'm talking about DED, which is itself a very tough work. And then you have to maintain certain SOD, standoff distance, to get the arc. So your SOD is fixed. So you cannot play with it to get the bead ironing or bead modeling or spreading. Your metal transfer can be in globular mode, can be in spray mode. So these are the few points you need to remember about the metal wire arc additive manufacturing process. If you're talking about metal extrusion process, then it's the same process. Pinch roller will be there to push down the wire. It will pass through the liquefier where the induction heating will be there, and the semi-melted wire. And in this case, it's definitely semi-melted, non-melted. Semi-melted wire will come out of the nozzle and get deposited over the build plate. There you can do anything: spreading, drop on demand, continuous, bead ironing, everything. But in WAM, it's not possible. So it's the welding that you need to study, and the same way you are going to use the additive manufacturing. So this is the shape manufacturing process where you divide your part into few shapes. So from here, the actual part is starting. So this is one shape. This will get deposited first, and then you will move up. Then this portion is almost same. So this portion will get printed. So this is based on how much complexity you have in whatever part, and based on which you are basically subdividing your part into few zones, and each zone is getting deposited in one way. Here the slicing is very important, how you're subdividing your part into few zones, and how you are going to deposit this zone, because this blue part is the support and the yellow part is the part. So you have to decide that first the blue will be there, blue will get deposited, then you are coming with the yellow part, yellow is depositing. Now again here the blue got deposited, then the yellow got deposited, then the blue, then yellow, then blue. This is how the shape uh, what was the full form, shape deposition manufacturing works. Again, it's very not very common process. Here you can see the parts which are getting printed and the way these are getting printed. how you have subdivided your part into few zones. First, you are depositing the support material like this, drop on demand. Then you are milling it to get the portion for the part to be printed. Then you're printing the part. After when it's finished, again you're doing the milling to smoothen it. Then you will deposit the support again, then the part again, like that. It's not like the actual or conventional 3D printing process. This is another example of a part. So in SDM, the slicing is very important. Processing each slice is also important, because here you are not treating all the slice equally. You are treating different zones differently, and each zone is having multiple slices. If you see this part, here is my first turn. So I will subdivide this part from here. This is my one. Now, then we have a next bend here. So this is my zone 2. Here we have the next bend. So this is my zone 3. So now how you're going to print? So first, if I print 1, then 6 and 5, both will be printing at the same way. Go. And then 2. So these 3 will be printed. After that, I can print the 3 and 7 together, or I can wait and then print the first 5 and then 3 and 7, and after that at the end we'll print the 4. This is the 1. Minimal precedence graph is, it says that I will go first 1, 2, 1, 6 and 2. After that, as this covers the whole area, then I'll print the 5 and 7. Then after that, I will meal the surface and then I'll print 3. After that, at the end, I'll print the 4. Then building tree expansion. So this is how you can decide which part to print first, and you can put the command in your computer accordingly. This is a bit not tricky, but a complex process and not like the conventional 3D printing. So if you subdivide this part, I can print this first. Then I can print this 5 and 4 and 2. After 2 is printed, I can print 6 and 3. And my printing is done. Or I can print first 4. First will be 4. And then I can start printing 1 and 5. After that, 1 and 5, I can print 2. After that, I can print 3 and 6. This is also one way I can print. Also, you need to check that if your minimal precedence graph, why it is important is because you need to see how many changes you are doing. That is one thing. You need to minimize the change of the tool, because when the support is coming, it will take some time. When the support will go, it will take some time. So that's why it is dependent that how you're going to uh, choose which path to go.
Ma'am,
These
does
are
the
few more.
horizontal line represent each segment?
Sorry, can you repeat?
Does the horizontal line represent each of the segments in this?
Yeah, so the part originally looked like this. Okay. And now I'm subdividing the part, as this is here. Here is a bend, here is a bend. So I just subdivide the part like this. And now I need to put the support. So this is the support and this is the support. Sorry. So now you can find out. So adjacent graph is like adjacently. So 4 is the first one. 4 I'll print. After that 1 I'll print. After 1, 2 and 5 print, and then 3. In case of minimal precedence, after 4, 1 I'll print. After 1, I can print 2. I can print 5. So if I print 2 and then I print 5, then I will be considered as minimal precedence. Sorry, my network was gone, so I left the meeting. Yeah, so for next week, you'll see morely on the wire arc additive manufacturing. So in wire arc, the heat transfer and mass transfer equations are gonna be more intense because there you are talking about metal, where you get the melting temperature, you get the uh, viscosity of the melt pool, you get which type of transfer, material transfer you're concerned with, globular transfer or spray transfer or continuous drop on demand, what type. Then you will be concerned about the conduction of the heat, how fast the heat is being conducted inside the part, because you will be considering the residual stress as well. So whenever you are talking about metal 3D printing, you are putting the heat source again and again. So your metal is interacting with the heat and then it's also moving. And when the part is finished, that particular line is finished, the heat is removed and your part is getting solidified very quickly. Because of this high heat gradient, high heat to achanak say stop the heat and then solidification, you get a lot of residual stress in your part. And because of the residual stress, you get the part to be more prone to crack propagation and crack initiation. So, because of which, it's very important to discuss about the heat transfer, conduction, viscosity, the how much heat will be reflected back, how much heat in case of laser reflection is there. So in case of arc there is no reflection, but establishing arc is much more difficult than working with the laser beam. So these are few points you need to be concerned about for the next week. So these are a few questions on the week 7 previous year, and I'm going to discuss this. So you guys can try to answer. If you have read the lectures, then it's fine. You can answer. Otherwise, you can just guess. Cool. We can start. So this is your first question. Consider the statement in SDM, one head is used for model and one head for support. In SDM, conventional slicing is done. So which one of the option is correct?
Only first statement.
Okay, the animation is little bit. So only first statement is correct because conventional slicing is not done here. Next is which of the following material are used for pinch roller in FDM? So it's hyperloop. Then, if a filament of 1 mm diameter is fed with 1 mm per second roller velocity, then it's at the feed rate is 5 mm per minute. So VF is the feed rate. So actual VF will be 5 mm divided by 60 to get it in second. And will there be any slip in roller? So there is one frictional coefficient used in the study, which is called this KF. KF decides that depending, as I said, depending upon your feed rate and the pinch roller rotation, you will get either the wire will break because of buckling, or it will buckle because of very high feed rate, or it will just slip in the roller. So the roller is moving, the wire is coming, but it's not getting squeezed because of the slip. So what will happen is dependent upon this KF. And the formula of the KF is this thing. So W and T is the width of the bead, T is the thickness of the bead. So the deposited bead cross section area is 2 mm square, which is already given. So W cross T is 2, VT is 1. This is VT, feed roller speed, basically. So you get the flow rate as 2. Now you put all the things in your formula and you get KF. As KF is less than 1, so the filament will sleep between the rollers. Okay. You can quickly write down this formula in your notebook. It will be easy for you during the examination.
Ma'am, if it is greater than 1, will it buckle?
No, it will not. It will not sleep.
Instead, will it break?
No. So if it's 1, then it will not sleep, and if it's more than 1, then it may buckle at the end after the pinch roller. Next is if the motor power required to push the melt through the liquefier is given by this formula. It's totally based on the formula that we have. So the actual answer is torque required for unwinding the wire is considered. This is the first statement. This is the formula. These are the like Kf is the friction factor, as I said. Del P is the pressure drop through the liquefier. Vt is the roller velocity. We already talked about the width and the thickness of the bead, and we have this P. Power required is Kf del P Vt Wt. So only one of the motor of the roller is driving. Higher filament diameter required higher force. Larger roller increases the motor power consumed. These are very general statements. So you can also guess from the options if you do not know the answer. The torque required for unwinding wire is considered. No. The pressure drop in the third zone is 30 ampere. If you remember, I have already told you the bigger formulas are important. So P1 is the pressure drop here, P2 is here, P3 is here, P3 is already given. If the flow exponent is 1, so here it's kind of a power law where 1 by m is the power and m is the exponent, which is 1 given here. Then pressure drop in zone 1. So this is the formula for zone 3, and you are already given with the P3 value, which is 30. So you can solve a little bit here, and L2 by L1, D2 by D1, and D1 is given here. So you can get little bit of it. Then you can write the formula for P1. You can replace this value in P1 and get ultimately the P1 as 7.5 MPa. No need to write this formula here because I already told you to read this P1, P2, P3 formulas from the PPT. If
Ma'am,
you
should
want,
we
you can.
by heart these
Yes.
formulas for the exam?
As this previous year question involves this problem, so I assume you can get some similar problems this year as well.
Okay.
I don't know the questions. I don't have any access to the question, but I can see the previous year questions. So the pressure drop in P1, P2, P3 is thus calculated. Next, we have which of the following is used as support material in microcasting? And second question is in SDM process, machining of the support is immediately followed by. Can you answer any of it?
Support material is copper.
Okay, so the after the deposition, we do the machining process and the support mechanism is copper. Next, okay. The dye swelling in FDM can be reduced by the carbon fibers, and in FDM, the final deposition bead shape depends on the viscosity of the melt. So if you remember that this thing, that depending upon the speed, you will get this shape of the track. It's also true that depending upon the viscosity of the melt, you will get the shape of the bead, whether it's this on the build plate or it's this. It depends upon the viscosity. Okay. Next, okay, in dye swelling in FDM can be reduced by ceramic particles and carbon fiber, mixing it with the powder with the wire. Then the flat road surface in FDM is obtained when we do the bead ironing. So bead ironing is when you put the nozzle in the layer thickness height, so that as soon as the this thing is coming out, this is already getting deposited and your bead is also getting ironed by your print head or print nozzle.
So
None
it
of
will
the
be flat. Is it?
yeah, none of ये इसमें आ गया, इसका option इसमें आ गया. Any degree of lag in the feed rate controller would result in either under or over deposition. Any degree of lag in the feed rate is basically how much wire you are releasing or how much wire you are giving to the pinch roller, and or how much roller is coming out of the pinch roller. And if there is any lag from in it, then obviously it will result in the under deposition. If there is lag in the feed roller and your print speed is also sacrificed due to that, there will be over deposition. So either of it. Okay, we missed this option. Bead ironing is basically print head is contact with the road surface, which I have shown here.
Second question, can you explain once more? 11th question.
This thing, okay.
Yes, ma'am.
So any degree of lag in the feed rate controller would result in. That means feed rate controller is basically if you have the pinch roller. अरे, ये क्या है? there is this pinch rollers and through which your wire is coming. So any lag means uh, the feed rate is not proper. When your feed rate is not proper and your print speed is very high, then there will be under deposition. Means you are not having very significant, the very sufficient amount of melted wire which is coming out of the nozzle, but your nozzle is at a high speed. So your deposition will be under deposition means you were expecting this much beat, but you are getting this much beat. This point you understand?
Because of the slow rotation of the roller, right?
Yeah, because of the slow rotation or your feeding is not proper, there is slip or not slip, but your tension is not maintained. Mainly it's because of the roller movement. Your rotation is not proper in the roller. It's less.
Okay.
So, and if the rotation, this velocity is not high, it's slow, and your feeding is not proper, then you can get the over deposition as well. Because there is lag in feeding means the wire has come. Now in between there is a lag. The wire is not coming. So your bead will look like this. Sometimes it's over deposition, sometimes it's under. Because you're
Okay.
feeding,
So
there is a
there will be
lag in the feed.
peaks and valleys will be there, isn't it?
Yeah. It's not peak and valley we call it as waviness. As you know, there is lot of the deposition rate in case of wire additive manufacturing is very high. Next, move on to the next question. So, the surface roughness is improved effectively by the solvent vapor smoothing. It's related to the support removal, so it's the memorizing question. Next, we have two filaments A and B of diameter dA and dB, respectively, of the same material, and effective length is to be printed using FDM. If the ratio of the critical pressure between pinch roller and liquefier to avoid buckling is this much, assume the hinge condition at both ends. Find the ratio of dA dB. So we have the bigger equation for the pinch liquefier pressure, if you remember. And then we have the pinch roller pressure also, like how much pressure you're putting so that it's coming to the P1. So now if we just divide these two equations, you get this dA by dB and you get this answer. You can write down this formula. This is a formula which is coming from two big formulas. You have just divided it. So it's better to note down these small tricks to solve problems fast. Okay?
And this liquefier will be coming below the pinch roller, right?
Yes. So surface roughness is improved effectively by machining and solvent vapor smoothing. Mechanical abrasion is also one. Mechanical abrasion is basically short blasting is one kind of abrasion, you can say. Sand blasting is also a type how you can avoid the surface roughness. Which of the following is true about FDM? So filament feedstock is in tension below the pinch roller. True. Filament feedstock is in compression above the pinch roller because you are putting the wire inside pinch roller. If you remember, your pinch roller is here and you are putting the wire. So it's not in tension, but it's in compression. your wire is coming. So this is in tension, this is in compression, and pinch ruler is below the liquefier. This is not true. Actually, this is wrong. Maybe it was misprinted.
Liquefier is below the pinch roller, right?
Yeah, liquefier is below the pinch roller. Which of the following is true about FDM? Okay, sorry, this question was misprinted 2 times. I can remove it later on. Identify the correct order. Minimal precedence graph, adjacent graph, and build tree expansion. No. Correct order means how you can get the final geometry by how you are basically uh, planning to print. So adjacent graph, first you will see what are the adjacent parts you have. You cannot print if your part looks like this. You cannot print this and then this and then this and then this. No, you have to find out which are the adjacent part. So these are the adjacent parts. So 1, 2 or 1, 2 you can print like. Then you have to find minimal precedence. Like you can change minimal and you have to consider this change at the lowest possible. Then build tree expansion. So basically, if you have this type of structure, so now you can think which one to print first. That is the build tree expansion that I can say 1 and 2. Like if you remember, we were writing like 1, then 2, 3. So build tree expansion is basically 1, then 2, then 3. You cannot print 2 and 3 uh, uh, simultaneously because both the nozzle will not work simultaneously. So first you need to print 2, then 3, or first you need to print 3 and then 2. So that is the build tree expansion. So this is the correct order how you need to identify how you're going to print in SDM. Okay.
Many choices will it come only in build tree expansion, ma'am?
Yeah, build tree expansion में many choices will be there.
Okay. The
But you
remaining
need to
two, only
see,
one will be there. Adjacent graph
yeah,
and minimal.
you need to see that how much energy you can save by not changing the tool much. Next, I have the minimum possible area of the deposition bead. So this here, the minimum possible area of the deposition bead in FDM is equivalent to the area of the 2 mm diameter circle. Then the standoff distance is given by. So if you see this question, this is the formula you can use for this. Minimal possible deposition area is equal to standoff distance square by pi. You already know the area of the diameter of the circle is 2. Sorry, if the minimal possible area of the deposition bead in FB is equivalent to the area of a 2 millimeter diameter circle, then the standoff distance. So the 2 diameter circle का area होगा pi r square, so pi 1 square. So like that, you get standoff distance equal to pi. And for the next
And
question,
standoff distance is B, right? B square by pi. In that B is standoff distance.
yes.
Okay.
So then the swell ratio is given and die opening diameter is given, then the swell diameter will be. So swell ratio equal to swell diameter by die opening diameter. So it's the easiest sum. You can just into multiply it and you get the answer. Okay. Then we have our next question. The ability of the material to neck down the bead cross section area to minimum varies based on the Weber number. This is also something you need to memorize, but when you will see the formula, you will write it down, so you will eventually memorize this. Short
Yes.
pinning is, yes,
It will depend on Reynolds number also, right?
I think. Yes, yes. So short pinning is used in SDM process to relieve the stresses. Short pinning is basically with a sand particle, Al2O3 SiO2 particle. You just put the particles on your part with a very high pressure, and the compressed air is carrying the particles and throwing it in your surface with a very high velocity and pressure. So that is the process of short pinning, but through which you can relieve the stresses. So these are the questions of previous to previous year, because I was a TA in previous year also. So these are the questions I was having. So we can just discuss about these questions as well, so that you can get more idea how which type of questions can come. For a given standoff distance h, the minimum possible area of the deposition bead in a fused deposition modeling based process can be given by A
H
mean,
square by
yes, h squared by pi. So then which of the following statements accurately defines the bead ironing in the FDM process? Contact nozzle is contact between the nozzle outlet and the freshly deposited bead. Okay. So the nozzle will be in contact with the freshly deposited bead. Select the correct statement made within the context of a shape deposition manufacturing process. Adjacency graph identifies the neighboring segment, and minimal preceding graph provides the build sequence. As I said, adjacent graph gives you which are the parts adjacent to each other. You need to identify that, and then minimal precedence will give you the build sequence by the minimal usage of the source resource. Following features of the SDM shape deposition manufacturing process makes the fabricated parts free from the staircase effect. So it's segmenting the part based on the visibility of the build and support material structure. Typical thermoplastic materials used in FDM is having shear thinning behavior. For FDM filament to be slipped between pinch rollers, can you answer this question? Just
KF less than 1.
it's less than one, as we have already done some on it. So in FDM, the nature of force acting on the filament between the pinch roller and the liquefier is, see, the questions are a little bit mixed
Compression.
up questions.
Compression.
Acting on pinch roller and the liquefier is tension. It's compression, the nature of force acting between the filament
Before
and the
the pinch
liquefier.
roller, it is
Yes,
tension.
yes, it's a tension and then it's compression. Under and over deposition of the thermoplastic material during the start and finish of a single bead in an FDM process, is attributed to the acceleration and deceleration of the print head during start and stop. So at the start, it's morely acceleration. At the end, it's mostly the inertia of the feeding of the wire. Then the microcasting process of SDM is a welding, and in which the substrate need to be electrode. two filaments A and B of it's again the same formula. If you notice, the diameter of it is 3 mm, 4 mm. So calculate the ratio of the critical force. Sorry, it's I think the other formula that I've put here. It's a mistake.
Ma'am, will it be the ratio of 3 square by 4 square?
Yes, 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 yes. The same formula that we discussed earlier. 3 square by 4 square. Then in FDM process, the bead ironing results in more stable, ensuring flat road surface. In SDM, if dash is used as main material, then dash can be used as support material.
Stainless steel and copper. First up.
Stainless steel and copper. Which of the following FDM-like process works on drop-on-demand principle? Is
Arbug.
the airbag. In the FDM process, if the standout distance is increased 4 times, then to obtain continuous deposition, the critical velocity will be. It's very easy formula.
16 times.
Yes, 1/16.
Means we use h square by pi, that formula.
It's 1/16. It's inversely proportional. Because when you increase the stand-up distance to get the same deposition, you need to decrease the velocity. So it should be 1/16. Instead of slicing the shape deposition modeling process.
Segmenting.
Sorry?
Segmenting.
Yeah, segmenting. Yes. Instead of slicing, we are not slicing it, we are rather than segmenting it. Which of the following FDM process has hybrid kinematics? Kappa, the company. Then the last question is in the context of FDM graph, which represents the relation between mass flow rate and viscosity. It's the first one. Okay, there is another question. So this is the total 8 segments are given for this SDM process. So which one you think it's good?
Option 4, ma'am.
Good. So it's first 8, then 1 and 2 and 3. After 3, we are printing the 7 as a support first, because if you see this two, it's a kind of tricky question when you are in time pressure. So if you see these two options now, it says after 3, you're printing 4 and 5. Now, if I'm printing 4 and 5, anyway, I cannot print the 7 because it's closed here. So the other way around. First 7 and then 4 and 5 and 6. Okay, so this much was what I was having as a PPT to discuss the previous year question. If you have any doubt, you can ask. Otherwise, I have some more questions that we can solve.
Ma'am, for the question in which you told that for a continuously deposited beam, if the standoff distance is increasing, that means to get the same deposition rate,
Yes.
like we should, the velocity will decrease, right?
Yes.
So in that question was in the question was it mentioned 16 or 4?
4.
So how it became 1/16, ma'am?
It's square. The square is also there, na?
Okay.
So that's why. I don't know where the question is. But you understand and understood the logic?
Yeah, because to get the continuous beam, if we increase the distance from the liquefier to the material that is deposited, then we should then the velocity will decrease.
Yes.
That's the reason, right?
Yes. To get the same bead because when you are moving up the nozzle, you're increasing the stand up distance. So your bead will be less in height and width because there will be thinning, shear thinning of the metal of the polymer, melted polymer which is coming out of the nozzle. To maintain the same thickness and width of the layer, you need to decrease the velocity so that more material can be deposited in a particular time. That is the logic. Okay, then I can start the quiz that I am having. Have you attended this quiz previously in any of my session?
Yes, yes, ma'am.
Then you know it's the Mentimeter. You need to scan this, and then the questions will come. Join. Have you joined?
I will join because my call was incorrect.
Sorry, your voice is cracking. Hello?
Yes, ma'am. I joined.
Okay, you join. Here it's not showing. Okay, game. Okay, so this is our first question. Let's see the right answer. So, the glass transition temperature is critical. Layer must remain above the TG temperature for fusion. TG, somebody has joined. I think. And also, TG defines the maximum service temperature of the printed part. How much you can print, how much temperature you can rise for that part. Okay. So, whoever has joined right now, if you want to attend this quiz, it doesn't have any marks. It doesn't have any marking or related to your examination. It's just to revise the concept, just to have more concept on the process that is going on for this week, which is FDM. So you can join this meeting. You have to go to menti.com in your mobile phone, then use this code to join this meeting. So it's a kind of a game where if you mark the answer quickly, you get more points. It's a kind of fun game. So Venkata, Ramana, if you are there, you can respond. I
Yeah,
think you are unmuted.
yeah, you muted only, but just I went to that,
Okay.
but it is not taking, I think. Yeah, questions 2 of 8. So here I have to,
You have to mark the right answer. I will press the enter, so you will get the question.
I
And
play,
as soon as you
press
mark
enter.
the right option,
Okay,
it will
it is
show.
giving us play ready.
Yeah,
Question
play
2 of
ready.
is okay.
Okay, here it's not showing me that you have joined. No worries, we can start and then see if the question is coming for you. Okay,
Okay.
see if the question is coming.
An FDM filament feeding system, the critical buckling phase can be estimated use. Orchard sphere.
So Euler's buckling load equation is used. The equation I couldn't put here, but you can get the equation from the notes. Let's see if you have marked it correctly. Why your name is not coming?
Yeah, but my answer is correct. Taylor's this one. But
You
why
are the
it is not?
barefoot.
Yeah, barefoot. Last
So
week
you are Venkata. But Anand was also there.
yeah, 676.
Anand, have you left?
No, ma'am, I am here only.
So your name is not showing here.
My name is also Barefoot Contessa, ma'am.
Oh, okay. Can,
So
can we start the test again and then we can change
Okay,
the name?
okay.
Yeah, that's why
some
it's not coming.
clash.
Clash in names. We can just
No
uh,
mention.
start the test again. And let's see if you can join the meeting again.
So
I can remove the result actually. There is a provision.
yeah.
Clear result. I'll clear the
So
result.
what is to be done, madam?
You have to just join the meeting again with this link.
What is
Not
to be
meeting,
done?
I mean this quiz. Present. Okay.
Searching for that.
Join. So here is your
Again, my
first
name
question.
is Barefoot Contessa, ma'am. This is automatically
Oh,
coming like that.
okay, no problem. Let's play. I think
So what is the
playing is more
answer
important
you
than the marks.
chosen earlier? Is it
I think we
Taylor's
also
this one?
started the game with the same name, so it's okay.
Sir?
First two questions we have already attended, so I am directly going to the next question, third question. So this is your third question.
Excuse me, ma'am.
Got it? So the main purpose of the French roller mechanism in FDM is to provide controlled traction force for pushing filament into the hot something is cut. Apply lateral compression to increase filament shear strength. Okay, debatable. So it's for the pushing the filament towards the liquefier. Then to apply the compression, it's not actually applying the compression force, but it's actually pushing the filament down. So I think third option is the better.
Control. I'm waiting.
Who gave which answer? Or both of you gave the same answer? Confusing. Okay. Fourth question. Everyone has voted. Yes, so the factor most strongly governs the maximum achievable extrusion force is coefficient of friction between driver gear teeth and filament. There is no point of seeing the result. Here is our fifth question. So yes, the viscous resistance of polymer melt flowing through the nozzle orifice is the thing primarily influenced because of the build during the extrusion. We have our sixth question. FDM critical force refers to oh, I forgot to put the correct answer. The maximum load the build plate can sustain. The maximum load the build plate can sustain? No, it's not the answer. The minimum compressive force required to prevent filament buckling. That is the correct answer. Then we have the seventh question. The temperature profile inside the liquefier is designed such that the gradual transition from solid to melt occurs to avoid excessive back. Back. Melt viscosity is minimized to prevent melt viscosity is maximized to prevent leakage. See, viscosity is there if you put the temperature, it's correct, but the gradual transition is there, which is forming because of the solid to melt occurs to avoid excessive the pressure drop That is also one thing. Next is the wire is coming from the pinch roller to the liquefier. If you put the heater in it and then you have the nozzle opening just above, adjacent to that, then you are just melting it and drop by drop it will fall onto the bill plate and you'll not have much control over it. So the gradual transition let you have more flexibility and let you have more uh, control over the
Control.
melting and deposition of this semi-liquid plastic wire.
It is like a semi-solid, no? Like toothpaste.
Yes,
From
yes.
toothpaste, how the paste will come out.
It's toothpaste kind of thing. We
Not
call
the
it melted wire, but it's actually not melted. It's the toothpaste texture.
yeah.
Here is your eighth question. Inadequate pinch roller pressure in the filament drive system is most likely to happen under extrusion due to slippage. Good. One person is getting all the points, whereas two persons are attending the MCQ. So now we have the ninth question. Increase extrusion force required due to higher melt volume rate. Correct. Yes, shear thinning. Okay. I think this week was a easier week, or you have already read, watched the lectures.
Haverstock.
It's the power law. I already discussed during the today's lecture that 1 by m power, that is the power law equation. This is our last question. During extrusion in FDM, higher nozzle temperature generally
So reduce viscosity, enabling smooth. Yeah.
yes. So only one participant, so one will win. Okay, that's all about today's lecture. This was all I was having. Uh, we will meet in the next class. Till then, if you have any doubt, you can email me anytime. Thank you for attending.
Happy Teachers Day, madam.
Thank
Happy
you.
Teachers Day.
Teachers Day, ma'am.
Thank you.